Hi, today's lecture notes. This video clip is about day 2 of our Algebra 2 Honors Summer School, where I'm going to talk about linear programming. Earlier in the lecture, we talked about linear inequalities, where you graph whether it's a dotted line or solid line, and you shade in below it or above it. We're going to use some of those practices to do linear programming. Linear programming is using a math model to come up with the best outcome of a situation. So there's 3 things to know about linear programming. You have an objective function. This is something that you either want to maximize or minimize. Sometimes it's called the optimization equation, the objective function. The feasibility region is an area on a graph that will show the constraints of the problem. So your objective function, you could probably plug anything into the objective function, but the only ones that are valid are the ones that live up to the constraints. So you might have a triangle, and if a triangle, just because it's the high point on the triangle, does not make it the maximum of the objective function. It means that it's part of the feasibility region. When you have the constraints graphed, you're going to use each of the vertices to determine which one of those is the optimum or the minimum. All of the maximum or minimum is going to be one of the vertices. Sometimes it's possible to have 2 vertices, like if you had parallel lines and another line going across it, you could have where there is no lowest number. You would still have 2 vertices that you could plug into the objective function. Let's take a look at this and see what we're talking about. Here we have 3 constraints, and these are what have to be lived up to be able to plug them into our objective function. This is what our objective function is. Now I've graphed these 3 constraints on Desmos. You can see this top line, we have a y-intercept of 2. That's this first one. If I divide both sides by 2, my y-intercept is 2. It's this part right here, this red line. The second one, where it's y is greater than or equal to, and my y-intercept is going to be 2 again. Let's see, 3 somewhere, 3, y, negative 3. That's this part right here. And then the third part is where my y-intercept is 2, but it's going to be this blue part, which is this part right in here. So what you have is this brown area, which is my feasibility region. Any of the answers that you have in this region will satisfy all 3 of these constraints. And you take those and you could substitute them all into this optimization equation. We are only interested in the maximum and minimum, though, so it's going to be occurring at one of these 3 vertices. And when we do that, it looks like this. I'll take my first one. I have the function of 0, 2, and I substitute that into the equation. You have 3 times 2 plus 0, and that's equal to 6. The second one, I'll substitute in 2, 0, and so I have 3 times 0 plus 2, and that's equal to 2. And then I have the function of 4, 3. And when I substitute in 3 for y, I get this plus 4 for the x, I get 13. Obviously, this one is the maximum, and it happens to be occurring at the top. It doesn't always have to be that way. It depends on what the optimization function is. And this one happens to be at the lowest. Again, it doesn't have to be the lowest point on my grid. What it has to be is the lowest value of this optimization function. Let's look at a couple of the word problems. Here you have 2 different blends of coffee are to be made. 75 pounds of Colombian coffee, 120 pounds of Brazilian coffee are available. A can of blend A is 4 ounces of Colombian, 12 ounces of Brazilian. Or can B is contained 8 ounces of each kind of coffee. The profit, this is what I'm looking for. The profit on a can of A is going to be 20 cents. So that's 20 cents for A. And then you have 38 cents for B. And that's going to give me my profit. That's what you're trying to maximize. This is my optimization function. This is what I'm trying to maximize. Now let's look at the constraints. We have Colombian coffee and we have Brazilian coffee. And it says here pounds, but I'm using ounces down below. So I'm going to change this pounds and this pounds into ounces. 75 times 16, I think that's 1,200, is the most of the Colombian that I can have. And 1920, I think is what it is the most of the Brazilian. We have 2 types of coffee, A and B. For Colombian, it's going to be 4 ounces of Colombian and 12 ounces of Brazilian. And for the plan B, it's going to be 8 ounces of Colombian, 8 ounces of Brazilian. So here we have a table that shows my constraints. And I'd also like to say that you can't have 0 ounces. So my A value has got to be greater than or equal to 0, and my B value, you can't have less than 0. So it could be 0, but it's not. It's got to be greater than or equal to 0. And we'll substitute in X for A. We'll substitute in Y for B. This would also give me my X axis will be the when we do a graph of this later, the X would be there. Now, I did a graph of these constraints on Desmos, and I came up with 1, 2, 3, and actually 0, 0 is another one of the constraints. If I were to, and this is using the constraints, using 4x, let me do this, 4x plus 8y has to be less than or equal to 1200, and 12x plus 8y has to be less than or equal to 1920. When I plug those in, I get these constraints. If you substitute each of these values into this feasibility region, you'll find that this is going to be the maximum, where I get my maximum profit. And it's a little bit more than this one. Here's a third problem that we looked at in class. Store owner wants to limit the payroll to $960. That's the amount that he can pay out. He's giving $4 an hour for regular and $6 an hour for overtime. Now, on the average, he makes, this is how much he gets. He gets $18 for regular hours, for the regular hours worked, and he gets $32 for the overtime hours. So they must be really productive during the overtime or making something really, really good or something like that. And this is going to be my profit. This is what I'm going to try to maximize. So I want to know how much money can I make. So this is my optimization equation or optimization function. The constraints at $4 an hour for regular plus $6 an hour for overtime, it has to be less than or equal to $960 because I can't pay out any more than $960. And it also says that our overtime hours are restricted to at most 2/3 of the regular time. So overtime has to be at most, it has to be, so my has to be less than or equal to 2/3 of the regular time. These are my constraints. Oh, also, I can't have 0 overtime. I can have 0, but I can't have less than 0. So this has got to be greater than or equal to 0, and my regular hours have to be greater than or equal to 0. So here I have 4 constraints, and I'm going to substitute those in. I've graphed this already using Desmos, and here's a picture of the graph. And I come up with this dark blue feasibility region with these 3 vertices. And I'll substitute each of those in to this optimization equation. I'll let you do it, and you can actually see then which of these will come out to be the best. And I believe it's this one. I'm not sure. I think it's this one if I remember. And that is all about linear programming. Good luck and success.